Welcome to Studi Live. In today's session on thermodynamics, we are going to talk about Carnot engine. This specific topic is a wonderful achievement. I said in the previous lecture that if you had a dream of achieving an engine that has an efficiency of 100%, no amount of energy being wasted, this is that. In Carnot's engine, this is by far the best engine that has been made. Not made, but thought of. It's a hypothetical. It's a hypothetical engine with principles and laws and everything working, but it is not practical. Until now, we don't have the practicality of this Carnot engine. Why? We'll talk about it when we understand the basic mechanics of what the engine is about. So in here, we've like very much similar to heat engine, we will be having a source at temperature T1. This source has to have a very infinite thermal capacity. That means it can withdraw. We can withdraw any amount of heat energy from it and it still will be maintained at the same temperature. This is our source T1. We'll also be having a sink E2. A sink also has a very high thermal capacity and I can add as much heat as possible into the sink without changing its temperature. The temperature won't change. Heat is being added, temperature won't change. Heat is being withdrawn until infinite times, but still the temperature does not change. That is the property of source and stand, and technically speaking, it is impossible. As for all the means that we know and all the physics that we understand, it is impossible to create a source and a sink as of now. At least now it is not possible. Maybe in after like hundreds of centuries, things might change, but now it is not. Here I have an insulating stand. Why do we need an insulating stand? I don't want any heat to be directly coming from source to sink. There has to be a separation. It's an insulating wall. It's a wall. I will be having my container with some working fluid over here. This container is supposed to have ideal gases inside. These are ideal gases, and if you are being true to yourself, you know ideal gases don't exist in real life. So almost everything about this Carnot's engine is hypothetical. It is not practical. But still, the mechanics that has been used to understand Carnot's engine and the efficiency, the practicality, the working of a Carnot's engine is impeccable. It is the best format of physics, theoretical physics that has been done with respect to engines. Okay, so let's start understanding about how Carnot engine works and what is the standard process. To be true, it is a cyclic process, and we're going to understand the entire process, the entire working of a Carnot engine in 4 steps. It is in 4 steps. Let's start with it. Let me draw the graphical representation, the pressure volume graph of a Carnot engine, and take it from me. This is the entire theme of the topic. In the Carnot engine, the graph is cyclic, as we all know by now. So this is what it looks like. Yes. This is the standard expression of the graph. I'll name this points as A, this is B, this is C, and this point as D. I'll also be doing a few more things. I'll be projecting these lines onto the volume axis. All of these points onto the volume axis. Why? We'll understand later. As of now, I'm doing some amount of work. It's K, L, M, N. Simple and easy. This is the Carnot cycle. What is this? This is the Carnot cycle. And the entire story revolves around this only. We'll be understanding all the 4 steps AB, BC, CD and AD in different measures. So let's talk about our very first cycle, AB. Let's talk about AB. Let's talk about this cycle AB. The cycle AB is nothing but a representation of isothermal expansion. Isothermal expansion. A to B. Please listen to everything that I say. At state AB, I understand that it has some amount of pressure, P, some amount of volume, let's say V, some amount of temperature, let's say T1. Initially, let's understand that the pressure is P1, the volume is V1, and the temperature is T1, initial state. Now, what is my job? My job is to take this container and put it on source T1. Initially, the temperature was T1. How did we get this temperature T1? We took the container and kept it on the source. We took the container and kept it on the source. The source is at a higher temperature. The source is at a higher temperature T1. So what happens is the gases inside will absorb this temperature T1 and they'll start expanding. The gases are going to expand, and until all the gases attain the temperature T1, we will not be changing anything related to this. Once everything is done, the gases expand, and then once the gases expand, the extra heat that was added to increase the temperature now falls, eventually balancing out the entire temperature, and therefore isothermal expansion. What it is? Isothermal expansion. Okay, initially I understand that the pressure, I'll just change this as PVT for technical reasons. Let's not confuse anybody. Initially it was P, V and T. But after I keep it on the source, these values becomes P2, P2 and T1. Why T1 constant? Because we are planning to keep the temperature the same. Any extra increase in temperature has to be removed. If I decide to calculate work, which can also be written as Q1, is equal to nRT1 log of V2 divided by V1 to the base E, natural logarithm. This happens to be my amount of work. This is when I'm talking about the state AB. If you want to calculate what this AB is, basically, all you have to draw and sketch, if you want to calculate this value, work 1, only using the Carnot cycle, you'll have to calculate the area from A, B, M, K, A. What is this basically equal to? It's basically equal to area A, B, M, K, A. This is what I want to explain. Correct? Next, let's talk about BC now. The term BC is basically about adiabatic expansion. How is it adiabatic expansion? Yes, we'll understand in a while, but it is about adiabatic expansion from B to C. What does it work? How do we achieve this? What do we now do is take this ideal gas. Initially what we did was taking this container on source T1. Now we are taking this container from source T1 and I'm keeping it at the stand. I'm keeping it at the stand. What happens now? The stand is an insulating material. So when I keep it on the stand, what happens is these gases start to cool down. These gases start to cool down, and when these gases cool down, I'll be waiting until the time these gases cool down and come to a temperature that is equal to the temperature of the sink. That is equal to the temperature of the sink. I'm going to take this. Initially what I did was keep it at the source. What I do next is keep it on the stand such that it achieves this temperature T2. What did I have? I had my pressure P2, volume V2 and temperature T1. I now converted this into pressure P3, volume T3 and temperature as T2. Until this happens, I now need to calculate work. I'll wait until this happens, and once this happens, I want to calculate work. W2 is equal to, it's an adiabatic expansion. It's an adiabatic expansion. So the work is NR divided by gamma minus 1 T1 minus T2. This is my calculated work. And if I want to calculate this on the terms of a graph, it's the area under the curve BC. So this area. You see this area? Yes. So if I want to also write it that way, it's basically area equal to BCNMB. Awesome. Great. Now let's talk about the third step, CD. Let's talk about the third step, CD. What do I do in a CD? I take this container from the stand and put it on sink. I take this container from the stand and put it on sink. In this case, it is going to be isothermal compression. What is it going to be? It's going to be isothermal compression. What about isothermal compression? I took this ideal gas and I'm keeping it on sink, which is maintained at a temperature T2. So what happens now is the gases compress. The gases compress. Now the temperature does not change because it is basic expansion and compression, where the temperature is going to stick at T2. The temperature is going to stick at T2. Initially, what was the condition? It was P2, sorry, it was P3, P3 and T2. Now what changes is P4, V4, but the temperature remains same, it is T2. The temperature remains same, it is always T2. Now if I want to calculate work, 3, it's Q2 and that is equal to nRT2 logarithm of V4 divided by V3. Did you get this? V4 divided by V3. That was about our isothermal compression. Now let's talk about our last, and if you want to calculate area, was it difficult? Now you know any graph under CD is your answer. It's CNLD. What it is? It's basically equal to the area of CNLD. Simple. Correct? Now let's go with the last process. The last process is very, very simple. It is from D to A, and D to A is basically nothing but adiabatic compression. What is D to A about? It's about adiabatic compression. Once I am done with the entire thing, what I do is I take the container again from the sink and keep it on the stand. In here, the container or the gases is kept on the stand. Compression happens. What happens is compression, basic compression happens. And now these values change. P4, V4, T2. They change back and they come back to its original position, to its original statistics, the original count, P1, V1, T1. This is adiabatic compression. This over here is adiabatic compression. And if you decide to calculate the work in this process, it's nothing very difficult. The work W4 is basically equal to adiabatic compression. That means the work that has to be used, the formula that we are going to use is coming from the work done for an adiabatic compression. It's nR gamma minus 1 T1 minus T2, right? So here we have T2, here we have T1. So this formula kind of validates its compression. So it's perfectly all right. So now we know that we do 4 forms of work. And if you want to calculate what is the area, it's area under the curve dA, that is this value. It's ADLKA. What it is about? It's about area ADLKA. Correct. Some people might ask, sir, what is the total work done in the process? Is it 0? The answer is no. Answer is no. The total work is not 0. How so? Let's do it now. The total work is W1 plus W2 minus W3 plus W4. You might wonder, sir, why a minus there? Why did you not write a plus? Because W1 and W2 is about expansion, whereas W3 and W4 is about compression. So if you compress something, the work is going to be the opposite nature as that of expansion. W2 and W4, they both are of adiabatic in nature. So with adiabatic compression and adiabatic expansion, the work is always same. If you remember well, with adiabatic processes, the work done is always same, even if it is compression or expansion. So I kind of assume that W2 and W4, they vanish away. What I'm left with is only W1 minus W3. Okay, let's focus on W1 and W3. If I talk about it, there are a few things that stay in common. Can I simply write W1 minus W3 as Q1 minus Q3? Correct? Can I just use these factors and I write it as NR T1 minus T2 logarithm of V2 divided by V1 minus logarithm of V4 divided by V3. Can I write it this? This happens to be my total amount of work done in a Carnot's engine. I hope you have understood this, right? We still are supposed to calculate about the efficiency of a Carnot's engine, but I'll keep that for some other day. As of today, I find Carnot engine is quite sufficient for you people to understand. Let me just revise this entire thing at a one shot. You have a source, you have a stand, and you have a sink. Source has an infinite thermal capacity, sink has an infinite thermal capacity. Any amount of heat can be withdrawn, any amount of heat can be absorbed. There is an insulating stand. That has nothing to do with it. It's just an insulator. We have a container filled with ideal gases. What we do first, we take this container, keep it on the source, then on the stand, then on the sink, and finally on the stand. Correct? So what do we do is we create a Carnot cycle, which is a cyclic process. This is a cyclic graph. It's AB, BC, CD, and D. We start focusing on AB first. When does AB happen? When you take this ideal gas and keep it on the source T1. Once you take this container and keep it on source T1, the gases will expand. Once the gases expand, the temperature gets distributed, the overall temperature falls. It was initially at a temperature P1, V1, T1. Now, since it is continuously kept on source T1, the temperature doesn't change, but the pressure and the volume will change. That's P2, V2, and T1. Calculate the work using isothermal formula, then go down to the next process. Next process is BC. BC, what you do is take this ideal gas from the source and keep it on the stand. And you'll wait until the temperature becomes equal to T2. You'll wait until the temperature becomes equal to T2. Once the temperature becomes equal to T2, you see these macroscopic variables. It was P2, V2, T1 in the initial start, but now it is change in pressure, change in volume, but a change in temperature too. Now the temperature has changed and it's an adiabatic process. What is the formula to calculate work? Nr gamma minus 1, T1 minus T2. I substitute things. We calculate the work done in an adiabatic expansion. A similar thing goes down with an isothermal compression. What happens? Now I take this container from the stand to the sink and this thing appears. CD appears. CD comes into action. The gas decides to compress. Since the temperature is lower, the gas decides to compress. Once the gas compresses, once temperature changes, the pressure, volume, temperature, all the parameters are going to change. P3 becomes P4, V3 becomes V4, and T2 remains same because we are at the sink. Yes? So W3 becomes equal to Q2. Q2, it is only because we are dealing with isothermals. nRT2 logarithm of V4 by V3, that is nothing but your area, CNLD. Then comes adiabatic compression, that is related to dA. When I talk about dA, I understand that the gas is now kept on stand. When the gas is kept on stand, it is going to come back to its original state. The original state was P1, V1, T1. And what is the final state? And what was the previous state? It was P4, V4, T2. So this expansion, this kind of compression takes place. And this is the formula for work in an adiabatic expansion. I decide to calculate the total work. Both of these, W1 and W2, are related to expansion. Well, these are related to compression. So W1 plus W2 minus W3 minus W4 is your total work. Okay, great. With adiabatic processes, the work done during expansion is equal to the work done during compression. So W2 and W4 is same. So the only work I am going to get is W1 minus W3, which is equal to Q1 minus Q2, which is equal to Q1 minus Q2. And if I substitute every parameter, this is what we get. This is our thorough final answer for work done in a Carnot's engine. I suppose all your doubts regarding a Carnot's engine is very, very clear. Over to the edge, I want to just add into the process that it is a hypothetical process. Such Carnot's engine, such Carnot cycle and such form of expressions are not possible in a real life as of now. Maybe in future, but until now, it is not a thing as of course. With that in mind, I hope all your doubts regarding a Carnot engine is very well done, and we will be meeting you people with many more videos in the near future. Until then, stay tuned with Studi Life and keep learning with me. Thank you.